have to get that bigger, I guess. Okay, let's see. Administrative issues of any kind. So apparently, I gather there was some sort of glitch at one point where the repository was out of contact with at least one of you. Did that? I mean, it seemed to be working this morning. That will happen from time to time, which is especially when 100 students pile on at 12:01 or whatever, or 11:59, and all simultaneously try to submit their job. Okay, good. In that case, I'll carry on. So, just a quick recap, since I redid a couple of these slides in ways that I gather are not going to be terribly visible. Oh well. The idea here was, again, we're going to fix recursive descent, fix all the problems with recursive descent so they can handle arbitrary grammars. That's the idea. And the thought was that we would just sort of start thinking about a function, parse, that given a non-terminal that you want to recognize and a string of tokens, an input string, tries to match that non-terminal to the beginning of the string and returns a value k. So that it's as shown in the diagram. The string that you're parsing is those characters or tokens C1 through Cn. And parse is going to return k such that those first tokens, C1 through Ck, are derivable from A. That's the idea. And so we went through showing how if you do this if you use a non-deterministic algorithm, a highly impractical non-deterministic algorithm, you can make it work, and the algorithm is actually pretty simple. I mean, maybe it looks a little complicated there, but if you just sit and meditate on that for a while, it looks like a pretty simple algorithm. It's just that there's that blue step up there at the beginning is a real problem. So we started looking at how you would do that. And the first step is to make this all recursive in such a way that we can memoize. And the way to do that, if you've ever, I think there have probably been, wait a minute, what's with this extra glare here? Seem to be another bunch of lights that are shining on my, no, none of this works. Yeah, where's it coming from anyway? There we go. One more, they have thousands of switches up there. Okay, so the idea here is, well, if you've ever done an exercise of turning a recursive program into in CS61A where you returned say a tree recursive program or a well, not a tree recursive program, but a linear program into a tail recursive program process, then the way that you do that, you might add some extra arguments to the recursive procedure so that you just sort of keep handing the thing off from one procedure to the other without having to do anything special with the returned value. Well, what we're going to do here is similar to that. We're going to break the parse procedure from the earlier slides into a somewhat generalized procedure that looks like this. First of all, we fix the string that we're working on. So this C1 through Cn is now the whole string that we're trying to parse. And now we write a little routine that will work on things in the middle of it, that basically takes on the middle of it. So when I parse I will parse not just a non-terminal, but I'll parse a particular production. I'll parse a particular production, a particular rule from that non-terminal. And my function looks like this. I give parse takes a rule and 2 positions in the string. And it basically says, we assume, first of all, when this thing starts, it assumes that all of these characters here, C, S plus 1 to C through K, have already been matched to alpha. So we know that those already match. And we are going to try, parse is going to try to match some of the rest of the characters, C sub K plus 1 up through Cj, with beta. So by match, I mean that you can start from alpha, which is a string, which is a bunch of symbols, and you can do those derivation steps and get CS1 through CK, and you can start from beta and get CK plus 1 up through CJ. And it's going to return the J. It's going to return how many characters, or the final character that's able to parse using this thing. And we'll have it do this non-deterministically, so it will be trying all possible paths. And as a result of that, this is going to be one of these recursions, as you can sort of guess from the form. This is going to be one of these recursions that gets infinitely big and goes traipsing down one path or another, and it gets really exponential really fast. So we're going to, in fact, in some cases, it even gets infinite really fast. So we're going to do something about that. Mainly, we're going to keep track of all the calls that we've made, and whenever we see something, whenever we see a repeated recursion, we'll just say, oh, wait a minute, I'm already working on that, or I've already computed that, so I won't do it again. So here is the function, which is basically I just took the original function and I adjusted it for these new arguments. So the new function is, when I want to do this parse, is I first of all look to see whether there are any, if there's nothing, if beta is empty, meaning that 0 symbols will take care of it, then I'm done. I simply say, okay, I'm done. We'll return K as the result. The last character that gets parsed will be K, so that's fine. Otherwise, beta has to start with some symbol. Let's call it X. Might be a non-terminal, might be a terminal, don't know. And then there will be some other stuff after the X. So if that X is a terminal, we just match it up with the next character of the input. And assuming that works, we continue. We call the parse routine again recursively, but this time we're already finished with the X. So we move that's why the dot has moved, because we've already parsed the X. And we're also moving to K plus 1 because we're done with character number K, and now we're going to try to produce K plus 1. And the symbol S, that is the place which is the point at which the beginning of alpha, the beginning of where alpha match, that stays the same because that hasn't changed. Okay. If the character doesn't match, then just as we did in the original algorithm, we give up. We say, sorry, my non-deterministic machine has fallen off a cliff. Poop, this path didn't work. Too bad. Now, the other possibility is that the first symbol of beta is a non-terminal symbol, in which case, well, we have this nice little routine sitting around that takes care of all of that case, because what that means is that we have to find some production for that non-terminal symbol. We find any production. We'll choose that non-deterministically. This is where the non-determinism originates. And we'll say, okay, parse that. We'll use parse recursively, and we'll look at the string and we'll ask, okay, parse the string C1 through Cn, starting at position. We'll start at position K, and we've parsed everything up to, but not including K. In other words, the empty string. We've parsed the empty string so far, and that's what matches the thing to the left of the dot here, the nothing to the left of the dot, and go to it. So it will return us a value that matches it will return the x that it matches, if it can. And once we have that, we then go on and match the thing after x. We match the thing after x, starting at whatever position it returned to us. You probably, all right, I talked through it slowly, but you'll probably have to go back and look at this. But after a while, it'll be clear that if you just knew how to do this thing here, the rest of it is pretty straightforward. You have to figure out, well, how would I really represent, if I were really writing a program, how would I really represent this thing? I mean, I've never seen any programming language value that looks like this exactly. So I'm going to have to come up with some internal representation for it. Like, for example, a pair consisting of the number of the production plus the position of the dot. That would be an example. And the rest of it is pretty straightforward. Now, the only problem is, how do we do this non-deterministic step? And how do we prevent the thing from doing a lot of redundant work and from going into an infinite loop in the case where you've got one of these weird cases where you have a right recursion or something, and you produce the empty string and all that sort of bad business. So as we started to do last time, we'll use a memoization table, which for historical reasons is called a chart. This goes back to the 60s when this kind of parsing, I think it was the 60s when this kind of parsing started. And the idea is that this, as with memoization, we'll have one entry in the chart for each possible set of arguments to the parse routine. And then the way that we'll do this is the traditional way to do that is to organize the chart into columns, so that you have k gives you the column number, and then the items in the column, and they're called items. That's actually the term. The items in the column contain the other two parameters, so that you get charts that look like this. All right, so here's k. Oops, got to remember to point at the right thing. Here's k along the top here. These are the characters that we're parsing, and these are the positions, and these are the values of k: 0, 1, 2, 3, 4, 5. And these are the chart items. Now, I claim, on the basis of just seeing this, on the basis of this idea, that you can demonstrate to me that this program must terminate. Why must it terminate? Any ideas? So I have one hand, two hands, always the same hands. These are the class ringers. We've got, come on guys, they're supposed to inspire you to, out of hatred for their way they keep putting their hands up every single time, you were supposed to respond by putting your hand. Didn't you ever see The Paper Chase or something like that? No? God. It's terrible. Of course, all my cultural references are 2 generations out of date, but okay, we're just not going to get any other response. All right, what do you think? And the number of items is finite because?
Because it doesn't have to keep on trying to either repeats itself and stops, or it will proceed.
Yes, but I mean, what is it that limits the number of items? What is it that limits the number of items, but the number of possible items that I can stick in these columns? Yeah. Right? Right, a finite number of rules, a finite number of positions for the dot. It can be either here, here, or here, for example. And a finite number of values for this thing, which is one of the numbers 0 through 5. So this thing must finish, and you can even tell what the bound has to be. The bound has to be the number of these things is going to be, say, the length of the longest right-hand side plus 1 or something like that, multiplied by the number of input positions, multiplied by the number of productions, and then, since there are that many columns, multiplied again by the number of input positions. So it's sort of the length of the string squared times a constant that depends on how big the grammar is. And then each one of these items can be looked at some finite number of times, and you'll find out that that turns out to be the length of the input again. And so you get a bound of n cubed, which is, you know, given that you're recognizing a grammar that where some of the strings might have an infinite number of matches, that's pretty good. N cubed is pretty good. So anyway, here's what it looks like when you actually run this routine. Now the way that you run it is that you start with what you're trying to do is to parse the entire string. So what you're asking yourself is there a way of parsing that string consisting of the input followed by the string on the right with this grammar, which means that in order for that string to match, you have to be able to start from the start symbol P. We always assume that there's a start symbol with a single production, that is the production that ends in the end of file symbol. So we have to be able to start from that, so we can seed the whole process with this thing here, which says, assuming that we haven't matched anything yet, the dot is at the left, and we are starting at position 0, right here. We are at position 0, and the empty string that we've matched so far also started at position 0. Can we get all the way through? When we get to position 5, will we have an item that looks like this? One that says, because what does this item say? It says, well, there is a alpha now consists of E followed by end of file, and it's an alpha that was produced. That's what alpha was, and that was produced by P. And it started at the beginning of the input, at position 0. That's what that 0 means. So the number here, the number in these columns means, the number at the top of the column means this is the character we are processing. This is how far we've gotten in the input. And these numbers here down the side mean this is the position at which that marks the beginning of what was matched at the beginning of this item. So this is where this particular item started, the characters that it started matching. So that's what we're after. So for example, this item here says that at character position 4, or at position 4, which is after the fourth character, we are immediately to the right of an E that started at position 3 and that consists of an S followed by an I, where an S and so that's what that means. And this last one here means that in column position 5, at the end, in other words, we are immediately to the right of an E followed by an end of file that started at character position 0. So that means we've succeeded. We've won. This string is in the language. Because this item is here, this string is in the language. And now the only question is, how is it that we got from one column to the next? And so the way that we did that, and you can go back and read the algorithm to make sure that it coincides with what I'm saying, is that we said, okay, well, let's look at each one of these guys in turn. We know this one, we started with this one. This one started the whole process. because that sort of described the initial situation. We hope that we are to the left of an E followed by an end of file, and we're in position 0. And it started at position 0. We're in position 0. Now, so then let's look at exactly what, let's see what exactly happens at this point. This chart, by the way, shows only the ones that succeeded, only the things that we actually needed, or that we actually used or could have used in the parse. So I've thrown away things that are that as it turned out didn't get used. So let's look at what this means. So we have this item here that just started things off. And this item, you see, starts with an E, which means that in the algorithm, we try to get past that E by looking at all the productions that E can produce, all the things that E can produce, and checking each one of them. So we had to check there are these 2 productions, one for E plus E, and one for S followed by I. We have to check both of those to try to get past them. So we threw those into the pot. And we also threw into the pot, and because, and then when we started looking at those, we saw, oh, look at this. Here's one that starts with an S. Here's an item that starts with an S. So we'll have to throw in the productions for S. Here's the one that we actually ended up using. There's another one. S goes to empty, but it turns out we don't use it in this case. So I just put in the one that got used. Now, when I put this guy in, this production right here, E goes to E plus E, well, that meant that I was immediately to the left of an E again. And so the algorithm would have produced another item, E goes to E plus E, and so on ad infinitum. But since it would have been the same item as I just created, it would be the same item as this one, our memoization function just says, don't worry about it. We're already working on that case. Let's not do it again. So that will take care of this first column. And now we process the first character, the minus. And when we process that first character, we see that which happens when we start processing this item down here, this call. Each one of these represents a recursive call to that parse routine. So when we get down to this call, we see, oh, this starts with a terminal symbol, finally a terminal symbol. And so, and it happens to match this minus, so we'll throw in a new item. It will start in position, it will have started in position 0, that's what this 0 is, but it will represent input, but the input at this point will be everything, will end at position 1. So we'll put the whole thing into column 1. And that's how we get this item right here. Oh, that's great. Okay, so that means that we're now to the right of an S, of a sign, of an S symbol. And since we're to the right of a sign, that means that we can produce, that one of the things we could do, it might not be the right thing to do, but one of the things we could do at this point is to say, oh, this could have been a production, S goes to negative, that produced an S. Okay, where did it produce an S? Where does this S go? Well, we look at this thing right here, this 0. It says, oh, well, this S goes to, this means that there is an S that started in column 0, or started at position 0. Oh, okay, so we'll go back here, and we'll look through our items here, and we see, sure enough, there it is. There is a production that was looking for an S. We were immediately to the left of an S. And it's the same item as this one, except that the dot has been shifted. So that means that we have discovered, this corresponds to us returning from the parse routine, we have discovered an S starting at the first position. So that means that, that we can take this production right here, and we can shift it, and bring us to this, and that allows us to come to this position, to this situation right here. where we have now passed the S. There's now an S to the left of us, and we're at position 1, so that we're looking at an I. Or we're looking for an I. So far, so good. Well, now, there's nothing to be done here. The parse is already returned from this, so the only thing that's left at this position is this item here, which means at this point we had better see an identifier, because if there isn't one, then we're all out of items. There's nothing else here that can possibly do it. So we'd better find that identifier. And sure enough, we do. Because the next input is an identifier. So that brings us to this situation. And now the whole thing repeats. This tells us that, well, there was an E that started at position 0 and it ends here. So we go back to position 0. We find this item here, but with the S at the beginning, and that's right here. It's this one right here. So we'll take that item and we'll say, okay, we're done with this item now. Here it is. We'll move it over here. I'm sorry, we'll move it. No, wrong. We're done with this item. We've parsed this E. So that's going to take us, that's going to mean that we go back here, we see, there's an E, here it is. In fact, there are 2 E's. But the one that works, the one that turns out to be the right one, is this one. We bring that over. And now the whole process continues. We're going to continue in that way, and if you just keep that up, you'll eventually get to this last column. But of course, there is some work that was wasted because you don't know what the rest of the string is going to look like. So in particular, there are a few items here that there should be some more red items. For example, right here, there should have been a red item for this guy here. The P goes to E dot bracket. But there are a number of other things too. For example, there's a red item here. S has a null production. So we should have added this production here. Or we do add that production because we don't know whether we're going to need it. We don't know whether we're going to need that production. And that production tells us that there's an S that started in column 0, and we're done with it. So we go back to column 0. Oh, look, we're already in it. And here is the we find something that begins with an S, and we bring that down here, starting in column 0. But that's not going to go anywhere because the next character turns out not to be an identifier, so we throw that away. So there are a number of these red items that get thrown away, and I can see now that I have left several of them off, so I should probably put them in as well. But that's basically the idea. This is basically the algorithm, and it's basically a technique for doing that recursive function in a memoized fashion, so that we limit the total amount of time that we have to work on it. Now it's rather nice, actually. This is not the most parallel thing you can come up with, but of course you see that we've got all of these items that are running pretty much independently. So you can imagine that a routine that goes and pursues a given item through the input or adds items to the input as it goes along. It is relative to some other parallel algorithms for parsing. It is kind of serialized. It goes one character at a time. But at the same time, although it doesn't have to. You could pursue this in parallel pretty well. But the only problem is that it's not what we call embarrassingly parallel. That is to say, you'll have competing functions adding things to these columns, and so there will have to be some synchronization. Still, I can imagine that you could do it pretty quickly if you really wanted to. The only problem, the thing is, of course, that parsing is actually very fast. And there aren't too many applications where you really need to do parsing so fast that parallelism is going to pay off very much. In this, I have a dispute with one of the other instructors of this course, who has been looking at parallel algorithms, who has looked in the past, I should say, at parallel algorithms for parsing HTML, because HTML parsing takes up a lot of time. My conclusion is that HTML parsing takes a lot of time because the people who wrote HTML parsers didn't know what they were doing. Okay, so this is Early's algorithm, and in fact, I actually have Early's algorithm or a program that runs it on the instructional machines, and so that you can fiddle around with it if you really feel like it. I'll make sure there's documentation. Documentation is there somewhere, but I'll have to refresh it. So it's kind of fun to play with. Why don't we take a brief break, and then we'll talk about adding semantic actions. But first, questions. I'm sorry, I have not been paying attention to you. You should, when I stop paying attention to you, you should shout when you have questions. Say ahem, or you there in the front, something like that. Okay, fine, let's take a break.
GSI's worked out how to run more on Cygwin?
On Cygwin, oh, good, that's right. That's the big one I haven't worked on yet.
I actually managed to set up M4 and all that fun stuff. I haven't actually tried to make it yet, but I just finished the installation.
You haven't tried to make it yet?
Well, learn to make file.
Oh, I see. Well, I'll be interested to know if it works. I mean, it's pretty. If you have a working Bison and Flex that are recent enough, I don't know what Cygwin has.
I just kind of installed it.
Yeah, I don't remember. That's interesting. Why don't you post your results, or if you're successful. If you're unsuccessful, then tell me. I think Dubois is working on has a Cygwin installation, and so he might be able to. He should be able to help you with that too. It would be interesting to see whether it.
I've been trying to, not because I'm married to Windows or anything. I could do it on Linux. I know it would be a lot easier, but I thought it would.
It'd be interesting to see. I mean, I can't think of any particular reason why it wouldn't work, but you never know. Cygwin does some strange things.
Well, they blame everything on Windows.
Yeah, well, I think the major problem is I don't know whether they are how good they are about the file name conventions. There are file name conventions, and you can also get hung up on new line conventions. Do they do something about new line conventions?
Not sure about that. I know my text editor handles new lines just fine, and I think if I just save it in Unix mode, it's fine.
I mean, do you see? I mean, it does. So it does. They don't try to throw away the return.
I don't know. I usually don't have that problem because I usually just put it in Unix mode anyway because I'll be transferring to the instructional. I don't think they've really yelled at me too much.
I mean, if there's probably a place in there, I'm sure there's a place in there where I forgot
there's a Flex,
check.
There's a Bison, there's an M4.
Yeah, I know there's a place in there, I'm sure, where I forgot to do the to remember to do the /r thing. So that will probably show up. But if you can get make check to work, that would be nice.
Okay.
So just let me know. Thanks. Okay, let's try to finish this up. So far all we've done is recognition. We can tell whether the string is recognized in the grammar or not. Now the next thing is computing semantic actions. Now the problem here is where you can get into trouble because, as I said, there are some cases where if a grammar is ambiguous, and we try to avoid those, of course, in programming languages, but Early's algorithm does work for ambiguous grammars, and when it does, there's this problem that, of course, you're generating, there will be choices as to what semantic values you can generate. It's much easier when you're just recognizing because you say, well, yeah, okay, fine, there are several ways to recognize. It just means that there are several ways to recognize. The answer is true. It's the same in any case. But the semantic value changes. The semantic value, you have to have, you now get a set of semantic values. And there are some weird cases, and you can, at home, you can work out what they are, where in fact you can have an infinite number of parses for something. As you might guess, this has to involve epsilon somewhere. But you can arrange weird things where there are an infinite number of parses. In Early's algorithm, the pure recognition algorithm will work just fine. It'll say, oh, this is kind of weird, but yeah, it seems to be in the language. But when you actually go to compute the semantic value, there's nothing you can do about the fact that there are an infinite number of values. The thing will have to run for an infinite amount of time, or somehow provide you a data structure that stands for an infinite number of values, or something like that. But we try not to deal with that sort of problem by just having languages that are not terribly ambiguous. And we'll assume from now on that that's what's going to happen. So the idea here is pretty simple. Every time you see one of these productions here, the ones where you've just finished a particular production, you've come to the end of a production, you can at that point, or when called upon, you can create a semantic value for that thing that you just parsed, assuming that all of the non-terminal symbols, that all the symbols in this alpha prime here have already had semantic values connected to them. It's just like with recursive descent compilers. So we can handle this with sets. That's what I just said. That's fine. But the idea here is now that when we do that, so going back to this example, what's going to happen then is that when we get to, for example, this production right here, whatever semantic action that we take, whatever semantic value we compute for S at this point, well, maybe something where we actually do some computation would be useful, like, for example, right here. All right, so this production, we're at the right of a SI. So whatever computation we do for SI, we'll assume that there is a value attached to S, such as, for example, -1. We'll assume that there's a value attached to I, such as, for example, 5, or whatever the value of I happens to be. And we do our semantic action thing, so we run that, whatever that production is, and that gives us, say, -5 or something as the value of E. So that tells us that there is an E, that this production here produced an E that started at position 3. So we go back to position 3. And, here it is, right here. SI started at position 3. Good, good. Okay, so that tells us at this point that we can attach the value, say, -5 to this E, and thus to all of the subsequent instances of this, all of the subsequent places where this E is used in the rules that follow. So there are more. There's a little more about that in the notes, but it's not. It's a little bit complicated, but it's a little bit tedious. But you can sort of figure out on the basis of first principles sort of how this has to work. Okay, so the problem with Early's algorithm is that, as you can see, the amount of space that we have to take up with this algorithm grows as the length of the string. And sure, it grows linearly. There's a constant factor having to do with the size of the grammar. But nevertheless, it does having to do with the size of the grammar. And it does not grow linearly, but it grows quadratically. But and that's perhaps undesirable. It would be nice if we didn't have an n squared algorithm where n is the input length. It would be nice if we had something better. So what actually happens, as we'll see, what Bison does, and Horn and all of these, the bottom-up parser generators, what they do is that they do a lot of pre-computation of these item sets. And for one thing, since there is no ambiguity in those languages, it turns out that we won't need this this symbol here, the starting position, because there will always be a fixed starting position that we know about. So we don't have to keep track of that. That, of course, drastically cuts down on the size of these sets. And it also turns out that these things are also able to determine all the possible sets of items that you can have, and thus we can make the whole process into a finite state machine. So that's that. But at their base, at their heart, you'll see that the things that Bison does, complicated, weird though it might seem, really make use of this concept, these item thingies, to do parsing. And that's sort of the reason that I went into this algorithm, which is actually the ironic thing is that this algorithm, even though it's much more general than what Bison does, it's actually a little less, in some ways it's simpler, because it's more directly tied to the grammar. So just as a little roadmap for the things that we're going to be doing in the next couple of lectures, my expectations are that you try to understand the concepts behind this, the intuition, the concepts behind this, and so that you can maybe step through a bit of Early's algorithm and some of what Bison does. I am not. Now that we have programs that do all of this for us, it's sort of less important that you be able to crank things out. But I do hope that you can get some conceptual understanding. The reason that it's useful is that the reason that it's of practical use is that when something goes wrong with your grammar, it's sort of nice to be able it will tell you about these sets of items, and it's sort of nice to be able to look at them and have some idea, based on what this thing is supposed to mean, have some idea of where the problem in your grammar is. So we'll see that. We'll see some specific examples of that in the next lecture or so. But this is basically the underlying machinery, or the precursor, I guess, of the underlying machinery that is used by the Bison program. All right, so that's sort of the very general. This is general parsing. So you now actually know the algorithm for parsing any context-free grammar. So this will work for any context-free grammar, and we are now going to specialize it to the context-free grammars that people actually use for doing programming languages. Okay, good. So we'll take that up on. Wait a minute. Is Monday a holiday? Isn't there a President's Day or something like that? Oh, that's all right. Fine. Good.